So this is the first of what I think are going to be two recordings, where I essentially cover two papers that I wrote recently. The first one has the title that I've given to the whole talk here: what is conditionalization and why should we do it? And the second one's really an addendum to the first one. The second one's called A Note on Deterministic Updating and Van Fraassen's Symmetry Argument for Conditionalization. Bit of a mouthful, but it essentially does what it says on the tin. It extends the ideas of this particular paper to cover some further arguments for conditionalization that I didn't consider in this paper. Okay, so what's the sort of overall message of the paper? Well, the idea is to look at this norm which Bayesians talk about called conditionalization. And I'll talk a little bit about what that is, talk about what Bayesianism is, talk about what conditionalization is in a second. But what I want to really do is take that norm, and I'm not really going to be asking whether or not it's true. I'm going to be looking at the particular arguments that we have for that norm, that we typically give for that norm. And I'm going to be considering 5 of those arguments. And I'm going to be asking, do the arguments really establish the norm in question? And in particular, I'm going to be pointing out that there's a particular assumption that each of those arguments makes, which I'm going to call deterministic updating. And I'm going to show that if you just take away that assumption, then the argument doesn't go through. But I'll also show that for most of the arguments, except in fact the most famous of them, there is some way of fixing them up so that they will still work without explicitly making the assumption of deterministic updating. So that's the structure of the paper. And the arguments that I'm going to be going through are pragmatic arguments, like the Dutch book arguments. They're accuracy arguments, like the expected accuracy argument. And then there's the symmetry argument due to Van Fraassen, which is really what that subject of that addendum paper is. So that's the one that's in the second, that's treated in the second paper. But in each case, it's the same idea. Each of these arguments, in order to go through, has to make this assumption of deterministic updating. And I'm going to claim that's not really a plausible assumption to make. It's not a reasonable assumption for the Bayesian to make. It's not really been justified. And then, as I say, I'm going to explore really how those arguments fare if you drop that assumption. But I want to start just here by saying something about Bayesianism itself, and then point out a little peculiarity of Bayesianism, which sort of, in a way, motivates the puzzle I'm interested in. Okay. So what's Bayesianism? It's really the epistemology of credences, or partial beliefs. So a lot of standard epistemology deals with a doxastic state that we sometimes call a full belief, or an on-off belief, or a categorical belief. That is a belief you either have or you don't. The sort of thing you report when you say things like, oh, I think it's going to rain tomorrow, or I think I switched the oven off when I left the house. Those are beliefs that you're reporting. They're categorical states. But there also seem to be doxastic states that we have that are not categorical. They come in degrees. So the sort of thing I report when I say, about 90% confident that it's going to rain tomorrow, or I'm as confident as not that I left the oven on when I left the house. Those states that we're reporting there, I'm going to call credences. So they're degrees of belief, strengths of confidence, you might say, and they're measured on a scale usually from 0% to 100%. Or sometimes when we represent them mathematically, we're going to take it as from 0 to 1. So 0 is just taken to represent your minimal credence, the lowest possible credence you can have. And 1 is meant to be your maximal credence. Okay, so that's what credences are. And Bayesian epistemology is really just a study of what the norms are that govern those credences. And standardly, the norms that have been taken to govern those credences are not entirely formal norms, but often norms spelt out in formal terms. That is, norms that don't pay an awful lot of attention to the specific content of the belief, but rather to some formal feature of them, like their logical form. Now, Bayesianism, Bayesian epistemologists have put forward a whole range of different norms that they think govern these credences. So, for instance, you might have a norm that governs how your credences in a disjunction relate to your credences in either of the disjuncts. Or you might have a norm that tells you how you should update your credences when you get a new piece of evidence. Or you might get a norm about how your credences in in a proposition about the objective chances should relate to your credences about some other propositions. You might get some norms that govern how you should set credences in self-locating propositions, so propositions like I am here now, or it is Monday, or something like that. But really, there are two core norms that just about all Bayesian epistemologists will sign up to, and then there's disagreement about which other ones should be added on top of those. And the two norms, I mean, I should say they're not totally uncontroversial. There are people who disagree on these, but the two norms in question are probabilism, which tells you something about how your credences in different propositions that are logically related to each other should relate to one another. So for instance, it does tell you something about how your credence in a disjunction should relate to your credences in the disjunct. So there's probabilism, and that's a synchronic norm. It tells you how your credences at a particular time, any particular time, should relate to one another. So it takes a snapshot of you at a particular time and looks at all your credences that you assign there and asks, are they structured in the right way? But then there are also at least seemingly diachronic norms, like how should my credence at an earlier time be related to my credence at a later time, where in between those times I've gained some new evidence. And it's really that latter one that we're going to be interested in today, and that's the norm of conditionalization. It tells you something specific about what you should do when you have a particular set of credences beforehand, and you gain some new evidence, and you want to update your credences in response to that evidence. Now, I mention those two norms partly because they're the core norms of Bayesianism, but also because they're oddly different in the extent to which they're permissive norms. So the norm that governs your priors, so these are the credences that you have right at the beginning of your epistemic life before you've gained any evidence at all. The credences that you have in those, the norm that governs the credences you have in those is super, super permissive. Even for people who add on a bunch of different norms, they often end up with something that's very, very permissive. That is, there's lots of different possibilities that you could opt for. There are going to be some people, objective Bayesians, who think, no, there's usually just one or some very, very tightly constrained set of possibilities. But most people, even if they add on a whole bunch of other things over and above probabilism and conditionalization, will think that that there's a whole range that leaves open really an enormous variation in the permissible attitudes you can have towards propositions in your priors. But that contrasts with the updating rule. So conditionalization is actually super impermissive. It basically tells you if you start off with this prior, pick your prior, get your evidence, there's a single thing that's permitted as a response to that. It doesn't say, oh, well, look, here's your prior, you get this evidence, and now here's this range of things that you're permitted to do in response to that. So it's very, very impermissive. And there's something sort of strange about that. Now, why do we accept this sort of oddity in Bayesianism? Why is this not more talked about? Why do people not say this looks like an unprincipled difference between the two situations, the constraints on priors and the constraints on updating rules? Most people, I think, would say in response to that, well, the arguments point us in that direction. We've got various arguments for probabilism and various arguments for conditionalization, and often the arguments for conditionalization are based on similar considerations to the arguments for probabilism. They're either sort of both Dutch book arguments, or they're both accuracy arguments, or they're both symmetry arguments, something like that. So there are, so we have arguments for each of these, and they'll just say, well, look, the arguments in the case of the priors just give these permissive norms. They don't say that we can say anything further about how to narrow down the set of permissible priors you could have. But they do say something very, very strong about what the permissible ways of updating are. And so we're just led by the arguments. That's all that we can do. In a way, that's the thing I want to undercut, because I want to say that actually, without making this assumption of deterministic updating, which I've mentioned before, the arguments don't actually give this very, very different view of the different ways in which one might update. In fact, you can get very, very permissive updating rules when you remove deterministic updating as an assumption. So actually, I think that the situation isn't so different. But as we'll see, there are certain sorts of things that you can do in order to try to recover it. And we'll come back to that later on. But I should say something now about just what conditionalization is. And essentially, I think, although often it's presented, often quite informally or roughly, as an updating rule which tells you how you should update your credences between one time and the next when you gain some evidence in the interim. So for instance, I start off with some credence, 50%, in the proposition that I turned off the oven when I left the house. And then as we're out for a walk, my partner says, who lives with me, says to me, no, I saw you switch it off, and when I walked past it just before we went out, it was off. Then on the basis of that, I update my credence, perhaps from 50% to 95%, that the oven is off. So, so that's often how it's presented. That's often how conditionalization is presented. It's as this rule that tells you how you should update your credences in response to new evidence. But actually, there are a number of, well, one thing to say is that the arguments that we have for conditionalization don't justify that version directly. That's what I'm calling here actual conditionalization, that version. And as we'll see, what our arguments in fact justify are planned conditionalization or dispositional conditionalization, which are the two other ones that I mentioned here. This isn't a new point. It's been sort of pointed out a number of times before. I think Fraassen talks about this, Brian Skirms talks about this, and so on. So this is nothing original here, but it's important to see that really what the arguments justify are the plan or dispositional versions of these. And then I will talk in a little while, after I've explained what each of these is, about how you might move from planned conditionalization or dispositional conditionalization to actual conditionalization so that you can in fact justify that, but indirectly. Okay, so let's meet them now. Here's actual conditionalization. This is the one that I said. This is the one that just says, look, it just governs how you in fact update on the evidence that you actually get. So suppose C is your credence function at an earlier time, T. C prime is your credence function at a later time, T prime. At the later time, T prime, your total evidence, that is the proposition that specifies everything that counts as your evidence. So it specifies, so yes, your evidence rules out everything that's outside E. So E is your total evidence at that particular later time, T prime. And your earlier credence function, your prior, let's say, assigns a positive probability to E. So you have non-zero credence in E. Then it should be the case that you should update your prior credence to get your later credence by conditionalization. What does conditionalization say? Well, it says that your later unconditional probabilities, your unconditional credences, should be your earlier conditional credences, conditional on E, the evidence that you gain. And we define that earlier conditional credences, any conditional credences, using what's often called the ratio formula, which just says that your credence in, say, X conditional on E is the ratio of your credence of the conjunction of X and E to your credence in E. So essentially what this says is your conditional credence of X given E is just the proportion of the credence that you assigned initially to E that you also assigned to X. Okay? So that's how you should update your credences according to actual conditionalization when you gain some evidence that you didn't assign zero credence to. Planned conditionalization is really quite different. Actual conditionalization was a genuinely diachronic norm. It considered your earlier credence function, C, and your later credence function, C prime, and it said how they should relate to one another. Planned conditionalization isn't really like that. In a lot of ways, it's really just a synchronic norm. It tells you not how your earlier credence function, your later credence function should relate, but how your earlier credence function and your earlier plan on how you would or would like to, or will, or intend to update should relate. So the idea is that at the earlier time you have two things, prior credence function, and then an updating plan, a plan that tells you how you're going to update given the evidence that you receive. So let's suppose you've got this earlier credence function, C is your credence function at the earlier time t. And also let's assume, and this is a bit of a restriction, well, sorry, I should say, some people think this is a bit of a restriction, other people think this is not in fact a restriction. Your total evidence at the later time is going to be from a particular partition. So there's some partition which gives all the possible evidence that you might receive. Okay, so it gives the partition gives your total evidence at the later time. So you're either going to receive, your total evidence is either going to be E1 or E2 or E3 or so on up to En. When is this sort of thing plausible? Well, the sort of case where I think it's kind of definitely plausible is the, I think everyone would say it's plausible, are the cases where, for instance, you're a scientific experimenter, you're about to run an experiment, and you know what the possible outcomes of the experiment are. So for instance, you've just put a particular chemical sample into a machine that has a digital reader, and that digital reader reads out 0.1, 0.2, 0.3, or 0.4. That's it. So you know that you're going to receive one of 4 pieces of evidence, or perhaps there might be a 5th piece of evidence where it doesn't read out anything at all, the machine's broken. But those are the possibilities. They're very limited and they don't overlap with one another and they cover the whole space. Some people, like David Lewis, seem to think that in fact that's fully general and it covers all ways, all situations that you're ever in. But other people, Jonathan Weisberg, Miriam Schoenfield, they have different views on that. Okay, so suppose you have this earlier credence function, then you have this situation where your total evidence at the later time is going to be one of the cells of the partition, E. And then R is the updating plan you endorse. What is an updating plan? Well, it's a plan that says, if E1 occurs, then I will do such and such. If E2 occurs, then I will do such and such. So if I gain evidence E1, then I'll do such and such. If I gain evidence E2, then I'll do such and such. So according to plan conditionalization, in that situation, R should exhort you to adopt a credence function, which is just basically the result of conditionalizing on the evidence that you receive. Dispositional conditionalization, very, very similar to plan conditionalization. But the updating rule is not that's in question, that's being judged alongside the credence function. The updating rule is not necessarily the one that you endorse, it's the one that you are disposed to follow. And you can kind of see how these might come apart. I might plan, I might think, oh, I've got to be actually really sober in my response to evidence. I must shift my credence in this just a little way upwards upon receiving this evidence. But in fact, I might have a disposition to be incredibly sort of extreme in my response to evidence, and I might actually, upon receiving certain evidence, shoot my credence up to near to 1. So what you plan and endorse quite different from what you in fact are disposed to do often. So they can come apart. So dispositional conditionalization basically says that the plan that you are disposed to follow should be a conditionalization plan. That is, you should be disposed to update by conditionalization on the evidence that you receive. So those are the 3 versions of conditionalization. And I'm going to say that if the arguments work, what they directly justify are plan conditionalization or dispositional conditionalization. And then we'll see in a couple of slides how you can move from arguments for those to arguments for actual conditionalization, the one that people in fact often state, but they need some extra philosophical assumptions. Okay, so here's the arguments that I'm going to consider, 4 what I call teleological arguments and an axiomatic one. Teleological argument, what does that mean? Strange way to put it. It means an argument where you judge the rationality of having a particular credal state, either a credence function itself or a plan to update in a particular way. You judge it by how well it achieves a particular goal or telos. In the first 2, the goal is to help you make good decisions. Okay, so it's often pointed out that there are kind of at least 2 different roles that credence credences play in your life. One is to sort of guide your actions, the other is to represent the world. So the first two, the goal is the one of guiding actions. And they're going to show you that if you don't, or they're going to try to show you that if you don't plan to conditionalize, or you're not disposed to conditionalize, then the credences that result will be less able to guide actions than they might well have been. They're suboptimal as guides to action. On the other hand, the accuracy arguments, which come later, say what the goal is not a pragmatic goal of guiding your actions, but it's a purely epistemic goal of somehow representing the world correctly. And so they have this different goal, and they show again that if you don't update by conditionalization, don't plan to update by conditionalization, then your credences will not play that role, not achieve that goal particularly well. And then finally, we've got a symmetry argument, which is not one where we talk at all about what the goal of credence functions are. Instead, it just lists a bunch of desirable properties that your updating rule should have, and then shows that, in fact, the only one that has them is conditionalization. But as with the other ones, it assumes deterministic updating, and then the question is, what happens when you don't assume deterministic updating? So a little bit about deterministic updating. I'm going to illustrate it by way of example. So here's the example that I give in the paper. You know that a hurricane is about to make, sorry, you know that a hurricane in fact has made landfall, but you don't know where it made landfall. You know that it was going to land in one of four places, either Panama City or Pensacola, both of which are in Florida, or Mobile or Biloxi, both of which are not in Florida. You phone up a friend who you know knows where the hurricane landed. They've been watching the news, or they're a meteorologist or something like that. And you say, where did it land? You ask, did it land in Florida? They're going to give you a yes or no answer. So what you're going to learn is either Florida or not Florida. The question is, how should you update your credences and the different possibilities based on that? So here's your credences down the left-hand side and the different possibilities. So credence 0.6 in Panama City, 0.2 in Pensacola, or 60% in Panama City, 20% in Pensacola, so 80% in total in Florida, and then 15% in Mobile and 5% in Biloxi, so 20% in total in not Florida. And then the question is, how should you plan to update upon receiving your friend's evidence of yes, no, Florida, not Florida? Conditionalization tells you, if you learn Florida, then you should move to the top right credence function, which assigns 75% to Panama City, 25% to Pensacola, nothing to the other two. If you learn not Florida, nothing to Panama City or Pensacola, 75% to Mobile and 25% to Biloxi. So you kind of see how conditionalization works here. It basically just says, look, take all your credence away from the options that have been ruled out, redistribute it over the remaining options in proportion to the credences that you originally had in those options. Or another way to put it is so that the ratios between the remaining options remains, the credences and the remaining options remains the same. So here you can see that before I learned it was Florida, I was 3 times more confident that it was Panama City. After I learned that it's Florida, I'm still 3 times, I think it's 3 times more likely that it's Panama City than Pensacola. And similarly, mutatis mutandis for if I learned not Florida. So that's conditionalization rule. And notice what it tells you is that you should update in a deterministic way. That is, upon learning Florida, there's a single credence function that is permissible as your response to that evidence. If you learn not Florida, there's a single credence function that's permissible as your response to that evidence. In contrast, here's a non-deterministic updating rule. So start off with the same credence function at the beginning. Same credence function, same 2 possibilities for evidence. But notice what happens when you get the evidence. If I learn Florida, I'm going to do one of 2 things. That's what my rule tells me. It doesn't tell me which one I'll do or should do. It just tells me I'll do one of these 2 things. The first one gives, both of them give no credence to Mobile and Biloxi. The first one gives 70% credence to Panama City, 30% credence to Pensacola. So it doesn't retain the ratio between the two of them. Second one similarly doesn't retain the ratio between the two of them. It gives 80% Panama City, 20% to Pensacola. And then if I learn not Florida, it's sort of the same two options, but flipped. So if I learn it, I'm either going to give 70% to Mobile and 30% to Biloxi, or 80% to Mobile and 20% to Biloxi. That's a non-deterministic updating rule. And notice, it's non-deterministic, and in fact, it never permits you to update by conditionalization. So it gives various options as permissible in response to evidence that you get. None of those options are the conditionalization option. In a nutshell, what I'm wanting to argue in a lot of this is you can't really rule out this updating rule using the arguments that we in fact have. So that's really what we're going to be arguing. But before I start looking at that, I just want to say a little bit about the move between plan conditionalization or dispositional conditionalization on the one hand, the thing that I think the arguments in fact justify, and actual conditionalization on the other hand. So how might you move from one to the other? So here's a way of moving from plan conditionalization to actual conditionalization. It needs some extra assumptions, and philosophical assumptions, I should say, nothing mathematical going on in any of these assumptions. The maths will come later on, but at the moment it's just philosophical assumptions. So the first one is, you always know the partition from which the evidence will come. Okay, so that's the thing that I said was kind of controversial. David Lewis thinks that is in fact always the case. Other people don't think so. When you know the partition, you must plan. Okay, so when you know what the possibilities are that spread out before you, you'd better make a plan about what you're going to do in response to each of them. Some people will think that's rational, some people not. I think Fraassen doesn't think that's irrationally required. Other people will think it is rationally required. Sort of think that that's sort of how we should go about our lives. Then there's a final step you have to make. If you do make a plan, when you make a plan, you must follow through on it. So this is a norm that in the philosophy of action literature, sometimes called diachronic continence, proposed by people like Michael Bratman, objections to it by people like Sarah Paul. But if we assume that, then we can get from plan conditionalization to actual conditionalization. Here is a briefer, and I think in a lot of ways much more plausible argument for dispositional conditionalization. Moving from that to actual conditionalization. I don't think I've seen this before. In fact, I don't think I've really seen an awful lot of discussion of dispositional conditionalization. A lot of the literature, including stuff I've written, has focused around plan conditionalization. Okay, so here's the argument from plan conditionalization, sorry, from dispositional conditionalization to actual conditionalization. The real only assumption is we in fact have updating dispositions. We are disposed to update in a particular way. So suppose I am in fact disposed to update in a particular way, so it's the case that there's some fact such that about me that grounds the fact that a disposition that says if I receive this piece of evidence, then I will do one of these things. If that's the case, then the actual updating behavior I have should be a manifestation. Well, will be a manifestation. That's not a should there. That's an empirical. Well, it's not really an empirical claim. It's sort of a consequence of this of one. The actual updating behavior. So actual updating behavior must be a manifestation of these dispositions. Well, if that's the case, and I in fact don't end up conditionalizing on my evidence, then that means I must have been disposed not to. But by dispositional conditionalization, that's irrational. So I'll have an irrational disposition. So there's something you can say that's irrational about me. So my way of updating, my actual way of updating, is irrational. Why? Well, it inherits its irrationality from the irrationality of the disposition that must have given rise to it. And then there's a sort of weakening of that, which says, well, look, even if you don't actually have these dispositions, it's at least true that you should be representable as if you have such dispositions, or representable as if you have such a plan. And if that's the case, then you might say that, oh, well, the irrationality of your actual updating behavior inherits that irrationality from the irrationality of any attempt to rationalize your behavior by attributing to you a plan or a disposition. Okay, so that's that's how you might move from plan conditionalization, dispositional conditionalization, to actual conditionalization. Now, before we get started on the arguments, yes, before we get onto the arguments we're going to be considering, let's have a look at the framework, the kind of formal framework that we're going to be working in. And then we're going to have to give some definitions. Some of those definitions are going to be fairly, going to have some technicalities to them. I think there's a way of kind of illustrating kind of what's going on so that people can understand, without following all of the technicalities, what they're like. But in a lot of ways, I think even if the kind of full technicalities of the results that we're going to talk about later on don't stick, the thing to really focus on is that example that I gave a few slides ago of the Florida, not Florida hurricane learning. It's really that second non-deterministic credence, updating rule. That's the thing you really can't rule out using the sort of arguments that we're interested in. We're going to be much more precise about exactly which updating rules you can and cannot rule out using these arguments, but that's the one really to keep in mind. Okay, let's go through the framework. But as I say, in a lot of ways, if you're not follow exactly kind of what's going on with all parts of the framework, the moral I'll try to sort of signpost a number of points can still be gleaned from it. Okay, so what's our framework? Well, we're going to just be talking about credence functions over finite algebras of propositions. An updating rule is going to be defined on a finite partition that is a subset of that finite algebra. So that is, there's a finite set of possible bits of evidence that you might receive, and each one of them is represented by a proposition in the algebra that you assign credences to. An updating rule on a particular partition is represented as a series of sets of credence functions. So basically, your updating rule is going to say, look, if you learn E1, then you should adopt a credence function from set C1. If you learn evidence C2, then you should adopt a credence function from set C2, and so on and so forth. Okay. That's what an updating rule, how we're going to represent an updating rule. So CI contains the posteriors that R endorses as a response to EI. And then a little bit later on, we're going to need a proposition which tells you, which says, look, you learned EI and you responded by adopting C prime. So for some particular response that are permitted. Okay, so that's some of the framework. I'll repeat those definitions as we come across them for the first few times. A couple of definitions. So deterministic updating rules, just what you would expect, given what I've said before. That is, if each of the CI, each of those sets of permissible credence functions that are permissible as responses to a particular piece of evidence, if each one of those is a singleton, if it just contains one particular credence function, then the updating rule is deterministic. It tells you, if you learn this particular piece of evidence, then there's this single credence function. That is, for every piece of evidence, there's some single credence function that's the only permissible response to that piece of evidence. Conditionalization, a conditionalizing rule for a credence function is just one that tells you should update by conditionalizing on any piece of evidence you receive when your original credence function assigned non-zero probability to that. So there's an example of a non-deterministic updating rule, but we've seen one already. In fact, that's just a kind of more schematic drawing of one, but the one that we saw about Florida and not Florida with the hurricane, that's a non-deterministic updating rule. And now we get to a little bit of a situation with a little bit of sort of technical stuff. I'm going to give a particular definition, and I'm going to give an equivalent definition for other people, both for people who might find the other one more useful. particularly because the second definition is really the one that's helpful for doing the maths, if you're interested in that. Could be that neither of them are particularly helpful for you, in which case I'll give an example and then try and give a kind of visual illustration. But as I say, even if at the end of that you're still not kind of fully on board with what is going on here, it's not absolutely crucial for getting the rest of the talk. The really crucial thing is just to keep that Panama City, Pensacola mobile blocksy example in mind. That's the one that's not a conditionalization rule, and that none of the standard arguments are going to be able to rule out without explicitly assuming deterministic updating. Okay, but here's a little bit more detail. So as well as conditionalizing rules, I want to talk about superconditionalizing rules. And it's going to turn out there are two varieties of these, because we can say slightly different things about each of them. A weak superconditionalizing rule is the following. So essentially what it says is, suppose you've got a non-deterministic updating rule. Then it might nonetheless, so then it's not going to be a conditionalizing rule. It's not going to tell you that for each piece of evidence that you might have received, you would respond to it by adopting there's a single credence function that would be permissible as a way of adopting it. There's going to be a number of them. But suppose we expand out the set of propositions that you have an opinion about, so that you in fact also have an opinion about how you will respond to the piece of evidence. You don't just have an opinion about the piece of evidence, you just have an initial credence in that. You also have a credence in how you'll respond to that initial evidence. And suppose it's the case that it's possible to expand out your credence function so that it does assign credences to these propositions about how you will in fact respond, in such a way that your new credence function that you have afterwards, each of the different permissible ones that you have in response to a piece of evidence, is not the result necessarily of conditionalizing on a piece of evidence, but is the result of conditionalizing on the stronger proposition that tells you not just what evidence you got, but also what credence function you adopted. In that case, we would say that your updating rule is a weak superconditionalizing rule. If it were possible to expand out the set of propositions to which you assign credences in such a way that it includes these R superscript C prime subscript I, to include each of those in such a way that whenever the extended credence function assigns positive credence to one of those, then the updated credence, the C prime, is in fact the result of updating this extended credence function on that proposition. Then it counts as a weak superconditionalizing rule. Strong superconditionalizing rule is really, really similar, but with one crucial difference. So suppose there's one of these extensions, you can extend out your credence function so that it assigns credences not just to the things that are assigned to before, the things in the algebra F, but also to these propositions that tell you not just what you learned, but also how you responded to it. It's possible to extend out your credence function like that in such a way that, in fact, it does assign positive credence to each of those propositions. And for each of the possible ways that you might update in response to the evidence that you receive, updating that way is in fact the result of conditionalizing that extended credence function on that proposition about the fact that you did update in that way. Then that's a strong superconditionalizing rule. So the difference between weak and superconditionalizing, the weak one doesn't assume that you assign positive credence to each of these new propositions that your extended credence function assigns. You could assign zero credence to some of those, in which case it doesn't tell you anything about what that updated credence function would be like. But whenever you do assign positive credence, then the updated credence function should be the result of conditionalizing the extended prior on that proposition. Superconditionalizing rule, it does demand that in fact you assign non-zero credence to each of these propositions about. So your extended thing thought that each of them was sort of possible, if you like, each of these ways of responding was sort of possible. So here's an equivalent definition for weak superconditionalizing. It looks kind of sort of complicated, but essentially what it says, what both of them are roughly are saying that your prior credence is some sort of weighted average of the possible posterior credences that you might update to upon receiving evidence. A little bit more precisely, in the weak superconditionalizing case, this is a sort of statement that's equivalent to the definition of a weak superconditionalizing rule. It's that there's a weighting for each piece of evidence you might receive and each possible response to that piece of evidence. There's some weighting, lambda c prime I, that lies between 0 and 1, inclusive. That's going to be important because it's going to change in the next definition. It could be 0 or it could be 1, such that those weights all add up to 1, such that your future credences are always certain of the piece of evidence that you learned. And secondly, your prior credence function is the result of the weighted average, is the weighted average of the various different C primes with those lambdas. That lambda and that final 2 there should have a superscript C prime as subscript I. In fact, just like it does now. Okay, so that's weak superconditionalizing, but just think about it as a prior should be a weighted average of the possible posteriors. In this, you're allowed the weights could be 0. Some of the weights could be 0. They've all got to add up to 1 together, so they can't all be 0, but some of them could be 0. And this first condition, this sort of certainty condition, what we're going to later on call the certainty condition, which just says that one of your posteriors, any response to learning evidence EI should be certain of EI. Now we're going to get the equivalent definition of the strong superconditionalizing rule, and it's just going to say basically exactly the same thing, except that you're not allowed to have 0 weights there. Every single possible posterior should get non-zero weight, should get a positive weight. Okay, so those are equivalent definitions. Let me just say a little bit about, try to give you a sort of little visual illustration of strong superconditionalization and weak superconditionalization. So here we're just imagining credence functions as kind of points in an n-dimensional vector space. It's going to be actually so think of a credence function as basically, think of the credence function as defined on an algebra. Think about the algebra just as kind of list of propositions. Then essentially the credence function is just a list of credences, list of numbers between 0 and 1 inclusive. So we can really take them just to be kind of points in the sort of n-dimensional unit cube. Okay, so but I'm not really going to illustrate it like that, not least because n dimensions, when n is greater than 3, is sort of tricky to illustrate. But let's just suppose they look like this. So here's your initial credence function, here's your prior, and here are your possible posteriors. Okay, so you've got, if you learn evidence E1, then you're either going to respond by taking C1 circle or C1 dagger. So those are your possible responses to learning E1. If you learn E2, then you're either going to take C2 circle or C2 dagger. Those are your possible responses to E2. This is going to count as strong superconditionalization because C sits within what's sometimes called the convex hull of C1 circle, C1 dagger, C2 circle, C2 dagger. That is a weighted average of them. So it sits inside those. It's inside the span, it's sometimes called. Van Fraassen's more of a fan of the term span. So that's strong superconditionalization. Strong superconditionalization insists that C sits strictly inside that span. It's not allowed to sit on any of the edges. Whereas weak conditionalization is going to say that it can sit on one of the, on one of the edges. We'll see that in a second. But here's just an illustration of strong superconditionalization. Essentially, it's the, well, not essentially, it just is the updating plan that we looked at before. It's the one about learning whether the hurricane made landfall in Florida or not in Florida. And notice here, I'll just leave this calculation to you if you're interested, the initial credence function, C, is just going to be the weighted average of those possible posteriors. So the one on the left-hand side is going to be the weighted average of the ones on the right-hand side with the weights that I've given down there at the bottom. So it's going to give a 0.4 weight to CF circle, 0.4 weight to CF dagger, 0.1 weight to C not F circle, and 0.1 weight to C not F dagger. So that means so none of those weights were 0, therefore it's a strong superconditionalizing rule. That's going to be helpful. So that's strong. That was strong superconditionalization. Sorry, this should say weak superconditionalization. So weak superconditionalization allows you to have. It also allows you to be on the interior, but it also permits you to be on one of the edges. Okay, so let's move on to some of the arguments. So like I said, the first 2 arguments are pragmatic, second 2 are epistemic utility arguments or accuracy arguments, and then the last one's an axiomatic or symmetry argument. So let's start with the first, probably the most famous pragmatic argument, diachronic Dutch book argument, famously given by David Lewis in a handout to a seminar at Princeton in the 70s, I think, published then by Paul Teller, I think, back then, but then Lewis just published the handout himself in his collected papers in the late 90s. So it's a very elegant argument, but as we'll see, I think it does assume, it does just assume deterministic updating, as we're about to see. Okay, so here's how it goes in the first place. So Dutch book arguments, standard sorts of things. One of the things your credences do is they require you to make particular choices. In particular, they require you to choose whatever option is presented to you that maximizes your expected utility. Now, of course, these are controversial claims. You're going to get certain people, Lara Bushak, for instance, who don't think it's rationally required of you to choose the thing that maximizes expected utility with respect to your credence function, because she also thinks that risk-averse behavior or risk-sensitive behaviors is rationally permissible as well. But standard Dutch book arguments don't take that into account. They just assume that's what you should, what bets you should choose when you're presented to them. Whether or not you accept a bet when you're presented with it is just whether or not its expected payout is going to be positive. Okay, so there's loads of stuff to say about whether that assumption is just wildly false, but let's just grant it at the moment. The real question is, does this argument, even granted those sorts of assumptions, does it achieve its aim? Okay, so here's a definition of incoherence. Credence function. So one thing to note about the diachronic Dutch book argument, it doesn't. It judges or evaluates a pair, both your credence function together with your updating rule. So it's not something that says, your updating rule is the thing that's at fault. It rather says the combination of your prior and your updating rule is the thing that's at fault. And it says these two things are incoherent, and incoherence is supposed to be a bad quality, and quality that if you have it makes you irrational. Incoherence if the following thing's true. There's a series of bets that you might make at the earlier time, and for each piece of evidence you might receive, a series of bets that you might be offered at the later time, such that the following thing's true. At the earlier time, your prior credence function would require you to accept each bet in the earlier series of bets. For each piece of evidence you receive, your later credence function that you would adopt were you to learn that piece of evidence and follow the rule, that later credence function requires you to accept each of the bets in the relevant later series of bets. And for each piece of evidence and each world that makes that evidence true, I've put the world in the evidence because I'm thinking of, say, these propositions as sets of possible worlds, but each world that makes that evidence true, then the combination of the earlier series of bets and the later series of bets that you would be offered in that situation loses you money at that world. So the thought is, there's a possibility that this kind of bookie who knows what your prior credence function is and your updating rule is, and now they've got a strategy to make money from you for sure. They're going to for sure offer you the set of bets B at the earlier time. Your credence function is going to require you to accept them. They're going to then wait to see what evidence you get at the later time. And at that later time, you're going to offer you this set of bets BI, if what you learned was EI, at that later time. And it's guaranteed that that strategy will lead to them winning money and you losing money. And essentially what Lewis did was he proved that if the pair, your prior credence function, your updating rule, is incoherent, just in case your credence function is not a conditionalizing rule for that prior. Okay, so that seems like a bad thing. So it looks like you've justified conditionalizing or planning to conditionalize or having a disposition to conditionalize, because if you don't, then you're going to be vulnerable to one of these Dutch strategies. You're going to be incoherent because there's going to be this strategy that a bookie could have for making bets against you that are guaranteed to lose you money. What if you back off from deterministic updating? Or what if you don't think it's required that your updating rule must be deterministic? Is there something that we can say about it in that case? Well, yes, there is. And here, just as before, we have two versions of incoherence. So just as we had weak and strong super conditionalizing rules, we have weak and strong notions of incoherence, and we're going to see that they match up in a particular way. Okay, so now we've taken off the assumption that the updating rule is deterministic. And we're going to say that the prior credence function of the updating rule is strongly incoherent if there's a series of bets at the earlier time, and for each piece of evidence you might learn, and each response, each credence function that your rule says is a permissible response to that evidence, there's a series of bets at the later time, such that, again, your prior credence function requires you to accept each of the bets at the first time. Whatever evidence you get and however you respond to it, that response requires you to accept each of the bets at the later time. And for each piece of evidence you get and for each world that makes that evidence true, you lose money. The combination of that earlier set of bets and the later set of bets is going to lose you money. So you're required to accept bets that lose you money. So again, there's a strategy that a bookie might have for making money from. Sticking with non-deterministic updating rules, or possibly non-deterministic updating rules, we also have a weaker version of that notion of incoherence. So prior and updating rules weakly incoherent if there's a series of bets at the earlier time, and again for each piece of evidence you receive and each possible response your rule permits to that piece of evidence a series of bets at the later time, such that again prior requires you to accept the earlier bets. Any of the responses required to accept later bets, relevant later bets, and then instead of just saying that the combination of those bets loses you money for sure, you say that the series of bets doesn't gain you any money and possibly loses you money. So for each of the pieces of evidence you get in each world that makes it true, the combination of those bets does not win you money, and that's for all of them, and for some of them, it loses you money. Okay, so then without deterministic updating, we get the following result. If your updating rule is neither weak nor strong conditionalizing rule for C, okay? So that means in our diagram before, if you remember, there was kind of four possible posteriors, two that were responses to E1, two that were responses to E2, and then we kind of drew the kind of shape between those. This first one says if your prior credence function sits completely outside that, then it's at least weakly incoherent and possibly strongly incoherent. It also says that if your updating rule is a strong superconditionalization rule, conditionalizing rule for C, then it's not even weakly incoherent. There's not even any sort of Dutch strategy for you, not even one that doesn't gain you money in all worlds and loses you money in some. So that would be if your prior credence function is sitting right inside that, in the interior of that. And then thirdly, if your updating rule is a weak superconditionalizing rule, so that is either sits in the interior or it sits on one of the edges, then it's not strongly incoherent. Okay. And remember, this one, the one I'm kind of encouraging people to focus on, that's a strong conditionalizing rule. So that shows, the second part of this theorem shows that it's not even weakly incoherent, but it's not conditionalization. So as I said, the arguments can't rule out this one. So the Dutch book argument's not going to be able to help us with that at all. Okay, good. So next argument up is the expected pragmatic utility argument. So in the Dutch book argument, you face decisions at the earlier time. Should I accept the bets? Should I not accept the bets? And also at the later time. Should I accept the bet? Should I not accept the bets? In the pragmatic utility argument, expected pragmatic utility argument, there's only a single decision that you'll face. And it's going to happen after you've received your evidence. So the thought is there's really three times. Earlier time, you've got your prior. Later time, you've received a particular piece of evidence. Final time, you face this decision problem. And what we're going to do is we're going to try to assign pragmatic utility not only to the options that you choose within, you might choose between in the decision problem, different possible worlds, but also to the updating rule that you use, or any particular updating rule. And it's going to do it as follows. What would be the utility of having a particular updating rule when you know that you're going to face this decision problem afterwards? Well, whatever happens, you're going to gain some piece of evidence. You're going to apply the updating rule. It's going to give you a credence function. That credence function is then going to allow you to choose between the options in that decision problem at the end of the at time t double prime. So you might think a good way to measure the utility of an updating rule to a particular world is to look at what option you would choose using the credence function that the updating rule recommends that you adopt, given the piece of evidence that's true at that world. And that's basically what we do here. So in this decision problem, I'm using the notation A superscript Ci, okay, to denote the option that the credence function Ci would lead you to choose, would require you to choose, the one that maximizes expected utility from the point of view of Ci. I should say there's a complication because sometimes there are going to be draws between them. In fact, there's ways of working that out, but I don't think there's any point in us getting into that here. So that's the idea, that you're going to evaluate how good an updating rule is by looking at how good the option is. That is, what's the utility of the option that your credence function would choose you to accept, the credence function that the rule recommends or demands that you adopt when you receive the evidence that's true at the particular world where you're evaluating the utility of the updating rule. Okay, and then we just get this nice nice result from that, that the updating rule that maximizes expected utility from the point of view of your prior is going to be a conditionalizing rule for that. This was really known. Savage already really has this in his Foundations of Statistics, 1954. I.J. Good sort of mentions it, alludes to it in passing as well. It was really made explicit and the proof sort of spelled out in Peter Brown's paper in 1976. But it's pretty clear that Savage had recognized it already. So that's the expected utility argument, expected pragmatic utility argument. Just to point out, notice in the Dutch book case, we judged the prior and the updating rule together as a pair. And so there was no sense in which it was the updating rule that was somehow to blame. It was the coherence between the updating rule and the prior. In this case, we hold the prior fixed and we use it to judge the posterior. You say, let's suppose I have this prior, which updating rule should I choose if I were to choose the one that maximizes expected pragmatic utility? So that's the form of the argument here. So that's all very well. If you assume deterministic updating, because then a number of times in what I just said, I said that the utility of the updating rule at a particular world is going to be found by looking at the credence function that the updating rule demands you adopt if you were to learn the evidence that's true at that world. But of course, if you've got a non-deterministic updating rule, there's no such thing as the credence function that tells you to adopt. There's a number of them. So how should you respond? And it turns out, and we're going to see this in the future as well, in the next few as well, there are in fact a couple of responses that you might make. What I call the fine-graining response or the coarse-graining response. So here's the fine-graining response. So remember, the problem is, at the moment, if the R is a non-deterministic updating rule, its utility at a particular possible world is not well defined, because that was supposed to be the utility of the option that your credence function would lead you to choose if it were the credence function that was demanded by the updating rule upon learning the evidence that's true at that world. But what if there's not a single credence function that the updating rule demands that you adopt? Then there's no, then it could be the different credence functions could recommend choosing different options when faced with the decision problem at a later time. So there's two ways to go. Either you can stick with the worlds that you have and then find some way of specifying, making that utility fine-grained. Essentially, what we're going to see in the next slide is you're going to be combining the different utilities of the options that the different permitted credence functions will adopt. And we're going to see the way that we will combine those. Or you can go this fine-graining route and basically change the possible worlds, change the worlds so they don't just specify what they specified before, namely the truth values of all the propositions in the algebra F, but also what evidence you receive, but actually that's already specified by W, but also what credence function you adopted in response to that evidence. Good, okay, so in this fine-graining response, we're going to specify both of those things. And then once you specify both of those things, if you fine-grain the worlds in those ways, then suddenly the utility is well defined again. What's the utility of an updating rule at a world where that world W fine-grained by also specifying that you receive evidence EI and respond by picking credence function C prime? Well, it's going to be whatever the utility is at that world of the option that C prime leads you to choose faced with the decision problem. And we can just show there that the updating rule is going to maximize expected fine-grained utility from the point of view of the credence function if and only if it's a superconditionalizing rule for C, where that means either a weak or a strong superconditionalizing rule. Okay. So notice, remove deterministic updating, you don't get conditionalization. So as I said, removing deterministic updating looks like you're not going to be guaranteed to get conditionalization. That's the sense in which deterministic updating is essential to that argument. But here's an interesting fact. I think it's interesting. If you go the alternative route, the coarse graining route, then essentially you do get conditionalization back, as long as you do the coarse graining in the right way. So remember what I said, the problem was that the utility of the updating rule at one of these coarse-grained worlds, the original worlds, is not well specified, because just specifying the world doesn't tell you, it'll tell you what piece of evidence you received, but it doesn't tell you what credence function you adopted in response to that. And so if you're going to keep that coarse-grained world that doesn't specify that, you'd better take all of the credence functions that you might adopt in response to that evidence, look at all the different options that they choose, look at the utilities of that world of all those different options, and then combine those together in some way into a number. An actual way to do that, of course, is to take the expected value. The expectation in terms of what? Well, here's a way of looking at it. Suppose I do have dispositions about how I will respond. So those dispositions aren't deterministic, but they are, I do nonetheless have them, they're probabilistic, they're stochastic. So a stochastic updating rule is one that comes equipped with a probability function that tells you, given a piece of evidence, how likely you are to respond to that piece of evidence by adopting credence function C prime. Then you can just take the utility of an updating rule at one of these coarse-grained worlds to be the expected pragmatic utility of updating in response to the evidence that you would receive in that world using that rule. So you just look at all the different things that that rule permits, that's all the C primes and Ci. You then say what the probability of you adopting each of those Ci is, given that you learn that particular piece of evidence, and you use that as a weight for the utility of the option that you would choose there. If you do that, then it turns out that your updating rule is going to maximize expected coarse-grained utility. That's what I'm meaning by this thing we've just defined from the point of view of your prior, just in case your updating rule is a conditionalizing rule for C. So the interesting feature here is that, in fact, there is a way out, that you can find an argument, a way of saving the expected pragmatic utility argument, basically by taking this coarse graining approach. Okay, let's move on to the expected accuracy argument. So here, so the expected accuracy argument is actually very similar in structure, if not in philosophical content, to the expected pragmatic utility argument. It essentially relies on the same piece of maths. So let's just see it. So essentially, here the thought is, rather than judging your updating rule, or better, rather than the goal of your updating rule being to guide your actions, it's to represent the world. So the way that we measure how well it's achieving that goal is by measuring its accuracy. And we're going to measure accuracy, just as is often done in the accuracy literature, by using a strictly proper scoring rule. I'm just not going to go into what the details of that are. That's something to look up elsewhere if that's something you're not familiar with. But essentially, it's the kind of agreed way of how we measure the accuracy of a credence function at a possible world. Okay, and then if we're in the deterministic setting, then the way of measuring the accuracy of an updating rule to possible worlds is really straightforward. It's very similar to in the case of the pragmatic utility argument. It says that the accuracy of an updating rule to world is just the accuracy of whatever credence function that updating rule demands you adopt if you were to learn the evidence that's true at that world. Okay, and then we have this lovely result from Hilary Graves and David Wallace in the mid-2000s, which says, look, your updating rule maximizes expected epistemic utility, or maximizes expected accuracy, or minimizes expected inaccuracy from the point of view of your prior, just in case the rule is a conditionalizing rule for the prior. What happens if we drop deterministic updating? Basically exactly the same thing that happened in the pragmatic utility argument case. That is, we can either fine grain, so that we specify not just the world, but also what credence function you adopted in response to the evidence that you received at that world. If you do that, then the accuracy of the the updating rule at a particular world at which you adopted C prime in response to that is just the accuracy of C prime itself. Sorry, that inaccuracy there should be the inaccuracy not of A super C prime, but of inaccuracy of C prime itself. In fact, just as I've corrected it to. So yeah, the inaccuracy of updating rule at a particular world where you adopt one of these fine-grained worlds where you adopt credence function C prime in response to the evidence you receive of that world is just going to be the inaccuracy of C prime at that world. And then you get, exactly as we got in the previous case, your updating rule R is going to maximize expected fine-grained accuracy from the point of view of your prior, just in case R is a super conditionalizing rule for your prior, where super conditionalizing rule is just either weak or strong. So super conditionalizing rule. Okay. What about happens if you coarse-grained? Basically exactly the same again. So if you stuck with the original worlds and with a non-deterministic updating rule, you took the expected accuracy of following that updating rule when you received evidence E prime. Sorry, EI, the evidence of that world. So the inaccuracy of the updating rule at the world is going to be the expected value of updating by that, where we have some sort of probability function, could be some sort of chance function that governs my dispositions to update in a particular way. Then you can adopt this. Then you use this coarse graining method. Then you're going to get this result that your updating rule maximizes expected coarse-grained accuracy from the point of view of a prior C, just in case your updating rule is a conditionalizing rule for C. Okay. Now, finally, we're going to, well, not finally, sorry, penultimately, we're going to get onto the diachronic accuracy dominance argument. So this is an argument that Ray Briggs and I gave a couple of years ago. Now, it's similar to the argument we just considered in that it takes the goal of credences and indeed updating rules to provide accurate representations of the world. But it's a little bit like the diachronic Dutch book argument in that it judges the credence function and the updating rule together rather than keeping the credence function fixed and judging the updating rule by its lights. So here we take the credence function and the updating rule together, and we take its inaccuracy at a particular world, just be the sum of the inaccuracy of the credence function of that world and the inaccuracy of the updating rule of that world. And when your credence function is deterministic, now usually your updating rule is deterministic, then Ray and I showed that it's going to be, the pair of them is going to be accuracy dominated, just in case the updating rule is not a conditionalizing rule for C. What does accuracy dominated mean? It just means there's some alternative pair, an alternative prior and an alternative updating rule, such that when you put those together, then their joint inaccuracy is less than the joint inaccuracy of your pair. What happens when you remove deterministic updating in this case? Well, actually, things are a little bit different from before. Suppose we go the fine-graining route, and we fine-grain our worlds by specifying not just the world, and therefore what evidence you receive, but also how you respond to that evidence. Then it's going to turn out that if your updating rule is a superconditionalizing rule for that, then it's not going to be accuracy dominated relative to fine-grained accuracy. But you're not going to get the other direction. So it's not going to be that all the non-superconditionalizing rules are going to be dominated in the way that you might expect by looking at the previous ones. Is in fact, there's going to be some non-superconditionalizing rules that are not dominated relative to this fine-grained accuracy. So in a way, this is our weakest result, because it shows that we can't even establish superconditionalizing as a norm for updating. So there are going to be some non-superconditionalizing rules that are not going to be accuracy dominated. Part of the reason for this is it's just super demanding to find a dominator, an accuracy dominator. really, really bad feature of something if it's accuracy dominated. And so in a sense, it's not too surprising that we're going to be able to find other things that don't have this really, really bad feature. Okay, so essentially the feature that we're getting at is a very extreme feature, the feature of being dominated. And so it's not surprising that fewer things have this feature. What's really interesting though is if we go the coarse graining route, then in fact we do get something very strong. In fact, we basically get conditionalizing. If we go the coarse graining route, it's going to turn out that if your updating rule is not a conditionalizing rule for your prior, then it is that that pair is accuracy dominated. There's some alternative thing that's that accuracy dominates it. So that's pretty interesting, actually. If you go the coarse grained route, in this case, you get conditionalizing, even though it's a really demanding sort of argument. This is really demanding to be able to find something that accuracy dominates you. Okay, so that's interesting. So that's the end of the teleological arguments. Remember, the teleological arguments were the ones where you judge the updating rule and the credence function effect, as it turned out in the Dutch book argument and in the dominance argument. You judge both of the parts of it by their ability to, or the extent to which they achieve a particular goal, a telos. Okay. We have particular ways of measuring how well they do that, and then we show that they sort of fall short if they're, well, the original arguments meant to show that they fall short if they're not conditionalizing arguments. And what we've been seeing is that if you remove deterministic updating, then you don't actually get that. Often you do get that superconditionalizing is required. If they're not superconditionalizing rules, then they'll fall short. But if you go the coarse-grained route, in all of them except the diachronic Dutch book argument, which doesn't really have a version of coarse graining, then you will in fact get conditionalization back. There are ways to get conditionalization back. There's ways to fix up these arguments so that you get it, but it's not. There are also other ways of trying to understand what's going on with these arguments that don't get that. So now we're going to move on to the symmetry argument. So the symmetry argument is an entirely different sort of argument. Instead of specifying some goal, some sort of some goal that your credences have, and then figuring out a way of measuring how well they attain that goal, and then figuring out that, and then showing that that if you don't update by conditionalizing, then you somehow do less well at that goal than you might have done. In the symmetry arguments, we just directly specify some properties we would like our updating rule to have. Just write down, I'd like it to be like this, I'd like it to be like that, I'd like it to be like this other way. And we show mathematically that there's only one sort of updating rule that has that property, and that's the conditionalization rule. The argument's due to Hughes and Van Fraassen, I think originally. That's kind of developed over various years. Grove and Halpern have a nice paper on this as well. So yeah, so that's the sort of structure of the symmetry argument. So let's just meet some of the properties that that we're supposed to assume. The ones on this first page, well, with the exception of deterministic updating, are supposed to just look super sort of plausible. So coherence, this just says that if you start with a probabilistic credence function, so one that satisfies probabilism, and you take a proposition that you have some opinion about, and you update, the rule should take you from that probabilistic credence function and the proposition learned as evidence and return a set of probabilistic credence functions. So basically it just says the output's got to be probabilistic. Deterministic updating, as before, just says that that set had better be a singleton. It should only have one thing in it. And certainty just says that if the piece of evidence that you learn is E, then each of the credence functions that you're updating will endorse it should be certain of E. So once you learn E, you shouldn't have like 90% confidence in E, you should be 100% confident in E. And then finally, here's the kicker. Here's the one that does all the heavy lifting. It's symmetry. And when it's stated informally, it looks really, really sort of plausible and perhaps clear. But then, as we're going to see, it takes a little bit of work to state it properly. So the way to state it informally is the way that an updating plan would have you update should not be sensitive to the way that the possibilities are represented. Now, possibilities here are the possible worlds. They're kind of the things that specify the truth values of the propositions that you're interested in. Now, what could that mean? Should not be sensitive to the way the possibilities are represented. Perhaps actually a better way of stating it is should not be sensitive to the grain at which the possibilities are represented, to the grain of the possibility. So, I can specify coarse grain possibilities or fine grain possibilities. Whatever they are, the possibilities have to give truth values for the propositions that my credence function assigns. Assigns credences to. But of course, you can, once you've got that, you can then fine grain those worlds, and they'll still, of course, specify the truth values for those propositions, but they'll also specify a whole bunch more. So if all I care about is only proposition I have any credence in is the proposition that will rain tomorrow, then you've got two worlds. You've got to have at least two worlds, one where it rains tomorrow, one where it doesn't. But I could also say it rains tomorrow and Mozart was left-handed. It rains tomorrow and Mozart was right-handed. It doesn't rain tomorrow and Mozart was left-handed. It doesn't rain tomorrow and Mozart was right-handed. That would be a fine graining of the original thing. So the point is, the way that the updating plan would have you update should not be sensitive to the grain at which the possibilities are represented. But what could that mean? We haven't really talked about the updating plan being in any way sensitive or even mentioning the grain at which the possibilities are represented. And basically, this is because the Van Fraassen framework is much more general. The updating rules that you have are not just updating rules for how to respond to a single partition. They're updating rules that should apply for any credence function whatsoever, defined on any, what we're going to call model, where a model specifies a set of possible worlds and a set of propositions over them, and algebra over that set of propositions. So an updating rule is an incredibly general thing for any set of worlds and algebra that I give you. It should tell, and then any credence function defined on that set of possible, defined on that algebra, and any proposition in that algebra, it should tell me how to update that credence function when you learn that particular proposition. So it's an incredibly general framework. Basically, what symmetry says is what the updating rule tells you to do when you learn something, when it's represented within one model and when it's represented within one finer grained model, should essentially agree with one another. Okay, so that's what that says. So let's suppose that we have a situation where one of the models, M prime, which has a set of worlds, W prime and algebra F prime, is a coarse graining of the other model, M, which has a set of worlds, W and algebra F. And what that's going to mean essentially is just that there's some surjective function that takes the possible worlds in W and specifies to give and takes them onto the possible worlds in W prime. So one way of just seeing this is really the possible worlds in W prime are sets of possible worlds from W. Okay, that'd be the way to think about it. And we've got a couple of assumptions here. You've also got to say something about how the two algebras are related. And the thing that we assume is just that for any proposition in F prime, so that is for any proposition that's in F prime, the inverse image of that proposition in F, inverse proposition of that is in F. So another way to, let's state that a little bit more clearly. So suppose you've got some member of F prime. That's going to be a subset of the coarse-grained worlds, okay? Now, what's the inverse image of that across phi? Well, it's just the set of possible worlds in W that phi would send into send to one of the worlds in that proposition in W prime. And it's just got to be the case that this was one of the assumptions that symmetry makes, that you're always going to have a proposition in F that represents that, or corresponding to that. And here's now just a definition. If you've got a credence function that's defined on F, then we also want to take the image of that credence function over in the other model. So one that's defined on F prime. So take a particular, so what, and so how do we specify that? Well, we have to specify what credence it assigns to a particular proposition in F prime. So take one in F prime, let's call it X again. We know from the point just above that there's the inverse image of that back in F. So the credence that 5C is going to assign to X is just going to be the credence that C assigns to the inverse image of X. Okay. It's not kind of crucially important you get this stuff, but I'm just spelling out in a little bit of detail. So what does symmetry says? Well, it says, look, there's two ways that I could go upon, if I have a credence function that's defined over a credence function that's defined over the fine-grained set, W and F, and then a piece of evidence in the coarse-grained set. There's two things that I could do. I could either, first of all, take C, apply phi to it, take the image of C to get phi of C, that's the thing that we just defined in the previous thing, and then update by using that piece of evidence that was defined on the coarse-grained world. And that would give me this, some set of credence functions, okay, that this updating rule recommends for someone who has credence function phi of C and adopts and learns proposition E prime. So that's one thing I could do. There's another thing I could do is I could take E prime and I could bring its inverse image over so that it's now something that C could update on. I could do that update using what the updating rule tells me to do with respect to that, and then I could take the image over to there, where the image of a set of credence functions is just going to be the set of the images of each of the credence functions. And basically what symmetry says is that those two things have got to be the same. So phi, so the image of what you did on the left-hand side has got to be the same as what you did on the right-hand side. Okay. So the set specified above that box in the top right and the set specified to the right of that box in the top right are meant to be the same. That's what symmetry says. It turns out conditionalization satisfies that. And in fact, what Hughes and Van Fraassen showed, that of all the updating rules that satisfy coherence, deterministic updating, certainty, and that symmetry, conditionalization is the only one that satisfies. Okay, but what happens if we drop deterministic conditionalization? Well, it turns out that we don't, deterministic updating, sorry. Then it turns out that we don't get conditionalization. I can actually illustrate that reasonably straightforwardly. So take any possible world and call the omniscient credence function of that possible world just the one that is certain of all truths at that world. So it gives credence 1 to all the truths of that world and credence 0 to all the falsehoods of that world. That's the omniscient credence function of the world. Now take the following updating rule. Take an initial credence function, learn a particular piece of evidence. What the updating rule says is just adopt as your one of the, so the set of credence functions that it says are permissible for you to adopt upon receiving that evidence is just the set of all the omniscient credence functions for the worlds that make that evidence true. Okay, so it's a set, well, as long as there's more than one world at which E is true, then that's a set. It's got more than one thing in it. It's going to satisfy coherence. Each of the omniscient credence functions is coherent. It's going to satisfy certainty. Each of them is certain of E because E is true at each of those worlds. And it's going to satisfy symmetry. That requires a little bit of fumbling around, but it's true. But it's not conditionalization. How are we to respond to that? Okay, so the argument doesn't give conditionalization if you remove deterministic updating. That's been the moral of all of these arguments. What are we to do about that? Well, it's not a hugely compelling argument as it stands against the Van Fraassen approach, because Van Fraassen Hughes could just say, well, yeah, sure. We were just looking for a kind of a small enough set, sorry, a small set, but that was powerful enough, set of properties that was powerful enough to specify conditionalization. You've taken one of our properties and shown that we don't get conditionalization. That doesn't mean that we couldn't find further properties that you could then add in instead of deterministic updating that gave it. They might say, we didn't have any problem with deterministic updating, so we never explored what the other properties might be, but if you have a bee in your bonnet about deterministic updating, maybe there's something we can do. So the question then is really, is there something we can do? And one way to see that there might not be is, here's 4 pretty plausible further properties, each of which seems desirable, but together with the previous properties we've considered, excluding deterministic updating, are not going to give you conditionalization. So stationarity just says that if you already are certain of E, then your updating rule should basically just return it should do nothing, should just tell you to retain your prior. Evidential regularity says that if you assign a positive credence to a possibility before updating and then your evidence doesn't rule it out, then the updating rule should demand that you assign positive credence to that possibility after learning. So it should never let you kind of adopt a future credence function that assigns 0 to something that you assigned some positive credence to before that hasn't been ruled out by the evidence. Responsiveness, it should be at least possible for your prior to make a difference to your posterior. So in that example that I gave before of the omniscient credence functions, it didn't matter what prior I started with, I'd still get the same set at the end. And finally, continuity says that small changes in the prior credence in E should not give rise to large changes in the set of credence functions that the updating rule endorses. Now this requires a notion of how large changes are in a set of credence functions. Turns out we can give one, a natural sort of one, and then it's going to be the case that the following thing is true. Adding all these properties together, leaving out deterministic updating, coherence, certainty, symmetry, stationarity, evidential regularity, responsiveness, continuity, still doesn't give you conditionalization. Does that provide further support? Well, it's sort of a difficult question, isn't it? Because I mean, it's going to be impossible to prove that there is no property out there that you would find plausible that when added to these other properties is going to give conditionalization. But it does sort of suggest that there are suggests that there aren't ones that you would easily think of. However, there is something which seems reasonably plausible. It's actually based on a principle that people often talk about, not in this context, but in the general context of updating rules. That is, in fact, entails deterministic updating. It's called strong order invariance. So strong order invariance says the following thing. Suppose you update first on one proposition E, and then you get a new, different piece of evidence, F, later on, and so your total evidence at the later time is E conjoined with F. Surely that should always give you the same result as if you updated first on F and then received evidence E, and so had total evidence E and F. That is, so looking at this diagram at the bottom, it should be the case if I start on the bottom left with my prior. I learn E, so I go up. Whichever I choose from that set, if I then apply and then update that by EF and get a further set, that should always be exactly the same set as if I first of all applied F, picked something from there, and then applied, and then learned EF. If you assume that, then you get deterministic updating. We'll see that in a second. So that looks reasonably plausible. I'm not sure it does seem so plausible. It seems very, very strong to say that, let's have a look at it again, whatever I choose the first time, if I update by E, and whatever I choose the time I update instead by F, then when I further go on to update by E and F together, I get this the same set of posteriors. I think really what's plausible is that it shouldn't be ruled out. Updating first of all on E and then on EF should sometimes result, should be possible that you end up with the same posteriors as if you update first on F and then on EF. I think that's really the plausible one, and that's not going to give you deterministic updating or conditionalization. So here are the results for this. Strong order invariance gives deterministic updating, so just substituting that in place of Deterministic updating in the Van Fraassen and Hughes theorem gives you conditionalization. Weak order invariance doesn't give conditionalization, and indeed, combined with all the other properties that we've considered, doesn't give you conditionalization. So I think, again, this is one where there does look like there's a way out for someone who likes conditionalization, but it's not mandated, I think. I don't think it would be easy to persuade people that strong order invariance is the correct version of order invariance instead of weak order invariance. So to wrap up, here's the sort of final summary. Here's the state of the nation. So down the left-hand side, we've got all the different arguments we've considered: diachronic Dutch book, expected pragmatic utility, expected accuracy, diachronic accuracy dominance, and symmetry. For the middle three, we've got two versions of each: a fine graining version, a coarse graining version. And then in the columns, we've got whether or not to justify superconditionalization, or just conditionalization, or just superconditionalization, or even that. As we see here, most of them will justify superconditionalization. Although, as we see, there are a couple that don't get us superconditionalization. In particular, the diachronic accuracy dominance argument, if you take the fine-grained approach, doesn't even get you superconditionalization. But on the other hand, so most of them do get superconditionalizing, but rather few of them get conditionalizing. Diachronic Dutch book argument, no hope. Symmetry, I think, doesn't, because I don't think that strong conditionalization is plausible. I don't think it's going to be plausible to argue in favor of that instead of weak order invariance. But perhaps you could do. In the other cases, there's one way to go that gets you it, namely the coarse graining way. But in the other way, you don't get it. So for expected pragmatic utility, expected accuracy, and diachronic accuracy dominance, if you go the coarse graining route, then you do get conditionalization. So there's a way of rehabilitating some of these arguments as arguments for conditionalization. My worry is that there's nothing mandated about going the coarse graining route, which is what you would need. So although in some sense it's going to be permissible to go that route and therefore permissible to get conditionalization, what we're really trying to justify is that it's mandatory to get conditionalization. So I think this assumption of deterministic updating is really particularly problematic. There's no particular reason why we should be mandated to take a deterministic updating route. We're not mandated that in our everyday lives. If I say, if it rains on Saturday, I'll do my laundry or I'll do a crossword, there's nothing irrational about what I've just said, about that plan that I've just made. Similarly, if I say, if I receive this evidence, I'll either do this or I'll do that. Doesn't seem to be anything irrational about that. Some people will say, oh yeah, there is something irrational about it, because your prior, by choosing your prior, you've already chosen your kind of you've made your inductive choices. You've already chosen within that prior how you should respond to evidence. Your prior doesn't just contain your current credences, but also somehow should contain within it how you should respond in the future. But I just don't think there's any non-question begging way of making that argument. It's not clear at all to me that within our prior credences should also be contained, should also be somehow encoded how we should update in response to that. Now, that a single particular way that we should respond to some evidence. You might say, well, look, by specifying your priors, you also specify your prior unconditional credences, you also specify your prior conditional credences, because, through the ratio formula. And therefore, you've specified how you should update. But of course, that's question begging. That just assumes that you've got to update by conditionalizing. If you've got to update by conditionalizing, that's absolutely true. If you pick your priors, then you have already picked your posteriors once you know what evidence you'll get. But unless we assume conditionalization, I just don't think there's any reason to think that. So that's the puzzle that I wanted to present for Bayesian epistemology. Thank you very, very much for listening.